Hello everyone, am I audible?
I can hear you.
Okay. So let's start today's tutorial session. First, let's recap the previous class skit part. So in yesterday's class, we talked about how to create quantum circuits and how to measure it and how to plot histogram. Then we create the Bell circuit also, and we we run it in local simulator, and then this is the local simulator, and then we try to run in real quantum computer. Let's see the results. We get our results. So if you see the jobs file and if you click the in 31 minutes, we did we run our circuit in real quantum computer. Then if you go to view more details, you can see we get the result. So in Bell in Bell state, we'll get 0011, but in real quantum computer, there will be some noise. Like here is we have some probabilities on 01 and 10 state also. So you can see the job status is also have successfully run, and the result is also shown here. And then we create also the 3-qubit Bell state, that is the GH state also in yesterday's class. So today we will look for some visualization tools in QIQT, and we will also try to implement DOS algorithm in QIQT also. So at first I will explain some visualization tools. Then Anuvab Nandi will explain the DOS algorithm theoretically. Then I will explain that in QIQT. So at first, let's go to a file. So let's try to plot the plot space in QIQT. So first we have to import some tools for visualization. So we are importing the plot blotch multifactor and the state factor. And there is some Then let's define our circuit is equal to quantum circuit, and the quantum resistor. Let's take one quantum resistor, then try to apply QIQT. Let's define the final state. Now we have lost. Now with this function, we are trying to plot this state. So here, that's how we can plot the this state. So at first the circuit was initialized in 0 state, then we applied the QIQT, and finally we defined that state in this function, state function, and then we plot this in plot space. That's how we can plot any state. So let's try to and another. Okay, let's try to plot in another state. Like if we apply Hadamard get, we know the final state will be the plus state. So around the x-axis. So let's see. You can see that. So that how you can visualize any state in QIQT. So let's try to plot any arbitrary state. So let's try to plot 1.0 state, any arbitrary state you can plot. That's how you can plot any arbitrary state. If you know the vector form of the state you want to plot, that you can plot that in. Okay. So now let's try to, if you have the spherical coordinate in plot sphere, can we plot that also, like we know the theta phi values. So if you know the coordinate, if you can plot that in QIQT, let's try it. So for this we need to import some function. So let's define the coordinate. And the radius is 1. So with this function, you can, if you know the coordinates, so you can plot also. So you can see, we know the coordinates, and you can also visualize this state. So there are other functions also to visualize. Let's try another function. Oh, let's define quantum circuit. With a single quantum resistor. Then let's apply atom. So now with this visualize transition function, let's try to visualize the state. It will take functions. So anyone have any questions? So you can see, you can slide this bar and you can visualize this. So you can see at start we are in a slide at 0 state, then we are rotating, and then the final state become the plus state. We know if we apply Hadamard gate, the final state will become plus state. So with these functions, you can visualize any states, quantum states. So we can also initialize this state also. So we don't need to start with 0 state. We can initialize our state to any arbitrary state. So let's try to initialize our quantum circuit. Let's define the quantum circuit. So we have two classical register and two quantum register. Consider initial state is 1 by root 2 and 1 by root 2. So with this initialize function, we can initialize any state. Let's try to draw that. We have to import the square root from math. Let's import the square root. Oh, I miss this slash. So you can see we can initialize it any like we want to initialize it 1 by so you can see we can initialize the state with this state. So but you notice we need to use the normalized state. If we use any normalized state, then you cannot use this. Let's try it. If we use any not normalized state, then you can see the sum of amplitude square does not equal to 1. So you have to normalize the initial state, then you can initialize any state. So now let's try to get the state vector. How can we get the state vector? Does anyone have any question? Okay, let's move on. Let's try to plot the state vector. So let's define a quantum circuit. Consider the first state was state 0. And so with this state function, you can get the state vector. Let's try to draw the state vector. So you can see we get the initial state. As we know, the in any quantum circuit, the initial state is always the zero state, that is in this vector form. You can write in latex form also. You can see we can write the state vector like this, and we can get the Bloch representation also. So you can see we get the Bloch representation of any state. So let's try to calculate the state after different operations. So at first, let's define a quantum circuit again. Now at first, the state, consider the first which is 0 state. Let's bring this initial state. So at first, that initial state, then let's try to apply a escape. Then consider this is the first state. And you can see the state will be changed, and can write apply x state, then you can, so with this visualization you can understand any big algorithm or any big circuit. You have to know the step. In every step you have to know the what was the state. So with this visualization you can get the state after any operations. So yeah, so let's move on. So in our last class we talked about the 3-qubit GHZ state. Let's try to, let's say, calculate any depth of a circuit. So if you see, so the depth of any circuit tells how many layers of the quantum gate execute. So let's, if we search it, if you search in Google and QIQT, then you can see with this QIQT documentation, you easily understand the depth of any circuit. So that's how this is layer 1, layer 2, layer 3, layer 4, layer 5. That's how you can easily understand what is the depth of the circuit. So it is very important. So when it comes to tell a circuit runs on a actual quantum computer, the number of gates is not only the important factor, that layer is the also an important factor. So that's how we can define depth of any quantum circuit. So let's try to see any circuit. Like here we have a quantum circuit and I operated these gates, and after that you can calculate the depth directly. Here you can see the depth is 6. But if you have circuit like this, so you can see the depth is 2 because the layer is here is 2. So why this is important? Let's try to make a 16 qubit 16 qubit entangled state. So you can see this is a 16 qubit entangled state, but here the depth is 16. So this takes more complexity and more time to run. So we need to reduce the complexity of the circuit. So how can we do that? So here is the, yesterday someone asked the question, can we make 3 or 4 qubit entangled states? So if you if you if you create this type of circuit, then the complexity will become very high. But you have to optimize the circuit. So how can we optimize the circuit? Let's see. So if we make a entangled circuit like this, so if you can see the full circuit here. So how did I optimize the circuit? This is a binary tree formation. So let's take such binary. So you can see this is the binary tree. So if you want to optimize any circuit, so here I use these parts, and then we this is similar to binary tree formation, so we can see here is the depth is 5. So you need also to optimize any circuit and to reduce the complexity. So Anuvab, Nandi will talk about these complexities, what is the complexity also, and what is the quantum. He will talk about the quantum algorithm part also in so so the Anubhav Nandi will take from here. Does anyone have any questions? So I am stop sharing now my screen.
Okay, am I audible? Hello, am I audible? Okay, okay. Thanks, Soumik, for introducing the concept of just a second here and go. Let me. এইখানে এইটা মাইক্রোফোন করা আছে
We cannot hear you. Could you unmute your microphone? But we can't hear you. I think, can someone confirm?
Yeah, we are looking into the matter. Just wait a few minutes.
Okay.
Hello, am I audible now?
I can hear you.
Hello. Okay,
I can hear
so
you.
are you guys able to hear me?
I can hear you.
Okay. Okay. Sure. Okay. Then let's continue. Let me share my screen once again. Okay, so let me repeat what I was saying for you once more. Okay, so in the last class, we had looked at this operator Rn chi, the unitary operator Rn chi, which is this general form which any unitary operator can take, a single qubit gate can take. So this we saw that it rotates the block vector by some angle chi about the n-hat axis. Okay, and so it looked like e to the power minus I chi by 2 sigma n, which could be written in this cos chi by 2 and sin chi by 2 form. And here we had seen that this is the general quantum gate we had seen, and we had derived it from the concept of generating functions in quantum mechanics. So we also looked at the concept of composite systems, and we had seen that if there is a system S1 which has a Hilbert space HS1 and a system S2 which has a Hilbert space HS2, then the composite system which is composed of S1 and S2, the Hilbert space of that, which we write as HS here, will just be a tensor product of HS1, HS2. And now the dimension of this composite system HS will just be a product of the dimensions of the subsystems. Okay, and in our specific case, we had a system consisting of 2 qubits. And so the Hilbert space corresponding to one qubit is C2, and the Hilbert space corresponding to the other qubit is also C2. So the composite system Hilbert space is C2 tensor C2. And since the dimension of this is 2 and the dimension of this is 2, so the dimension gets multiplied, and this is a 4-dimensional space. Okay. And we saw that when the Hilbert space gets tensor product, the states of the belonging to the Hilbert space also get tensor product. And although we, this for C2, it is a 2-by-1 column matrix, the individual elements. When you take the tensor product, you get a 4-by-1 column matrix. So here and similarly, you can all the operators like sigma z, for example, they also get tensor product. And similarly, all the sigma z is a 2-by-2 matrix individually. So when we take the tensor product, we get a 4-by-4 matrix. And I had introduced you to the rules according to which we take the tensor product. And the tensor product, oftentimes we like remove this tensor product sign. We just, so when there is ket psi tensor ket phi, we just write it as psi ket phi. So the tensor product sign here is understood. Now, we also saw that this 0 tensor 0, 0 tensor 1, 1 tensor 0, and 1 tensor 1. So here this tensor product is understood. So this forms one basis in the C2 by C2 space. And so if we have a basis in some space, then we can take a linear combination, any arbitrary linear combination of those basis states and form a new state. So for example, we have formed the state psi over here, and we have taken a linear combination of this 0, 1 and 1, 1. Okay. And here you can see, we had seen that in some of these states, we can take, say here 1 is common. So you can take 1 common out as tensor 1, and you can write this as 1 by root 2 0 plus 1 tensor 1. So so it can be written in some psi tensor phi form. So all those states we had said that which can be separated out in this form are called separable states. And but there are some states which cannot be written in this form. And we had seen some examples like 1 by root 2 0 0 plus 1 by root 2 1 1. So here you cannot take anything common out and write it as this. So this state is an entangled state. And in the 2-qubit scenario, we had looked at some quantum gates. And a special gate that we looked at was the controlled NOT gate or the CNOT gate. So here we saw that if, so there are 2 inputs and 2 outputs. So this first input remains unchanged, and the second input becomes, so if there is X and Y here, so here X and Y are just ket 0 or ket 1, then you can find that you in this output, in the second output, so let's say qubit 1 and qubit 2. So qubit 1 remains unchanged, but qubit 2, it becomes X XOR Y. So this is the controlled NOT gate. So why is it controlled NOT? Because when X is 0, then Y stays unchanged. So if there is 0 and 1, then it will just it will remain 1. But if X is 1, then Y flips. So say X is 1 and Y is 1, then Y flipped to 0. So that's why it was also called the controlled NOT gate. Now, we also looked at how to generate entangled states, in particular the Bill states. So we saw that if you apply a header mode and then a CNOT, so header mode on the first qubit, and use that qubit as the control of the CNOT gate. So remember, this was known as the control qubit, and this was the target qubit. So if you apply a header mode, then a superposition will be generated. And if you use that superposition as the control of the CNOT gate, you would get the unentangled states. Remember, we have started from a separated state because 0 tensor 0, it is already in the psi tensor 5 form. And then we reached an entangled state, which cannot be written in the psi tensor 5 form. And in particular, we had looked at these four entangled states, and we called them the Bill states. And they are similar to the 1 by root 2 0 0 plus 1 1 with different phases and different combinations. So the ones which have, we also saw that the nomenclature is affected by this. So when you start with 0 0, you get this. So this is called beta 0 0. And similarly, if you start with 0 1 in this circuit, you will get beta 0 1, 1 0, you will get beta 1 1 0, and so on. And also there was another nomenclature like in terms of phi and psi. So we saw that whenever there is 0 0 and 1 1 involved, it is phi. Now this plus or minus implies whether it is a plus superposition or a minus superposition. For example, phi plus here gives you a plus superposition, and phi minus is a minus superposition, both containing 0 0 and 1 1. So 0 tensor 0 and 1 tensor 1. And phi are the ones which contain, sorry, the psis are the ones which contain, oh, sorry, I think I have written this wrongly. So this is 0 1 plus 1 0. Huh. So psi plus, for example, you see this will contain 0 1 and 1 0, a superposition of those states. And if it is plus superposition, then it is psi plus, and if it is minus superposition, then it is psi minus. Okay. So, and we had ended, like a lot of you had the question that how to implement AND OR gates or classical gates with the help of quantum gates. So we will start today's session with this by answering this question. But apart from that, if you guys have any questions about this part, which we did yesterday, please tell me. So till this, is it all clear? All okay? Am I audible?
I can hear you.
Okay, okay, sure. So I am assuming that this part is clear. So let me start with the the next
Sorry,
part. So let's
did you deliver yesterday some training or some tutorial?
no, not yesterday really,
Oh,
but
okay.
this is the content that we covered in last class, and the
Okay.
last class was when 31st May.
Okay.
Okay, so yeah, so if you have missed that, you can go back and check once. Okay, so any other questions? Okay, so let's start with CC. So let's so in order to understand how to implement AND OR gates like other classical gates in a quantum circuit, we have to introduce another gate, which is the CC NOT gate, or the full form is controlled NOT gate. So there's two controls here. Right. And this is also known as the Toffoli gate. And so if you have this, then it is a 3-qubit gate. So there are 3 inputs and 3 outputs. The last qubit is the target. So basically the 3rd qubit. And the first 2 qubits are the control. Okay. Now, so how does this work? So this works similar to the controlled NOT gate, but there was only one control, and here there are 2 controls. So if both A and B are 1, so in controlled NOT gate, if the control was on, then was 1, sorry, then the target was flipped. So, but here you need both the controls to be 1 in order to flip the target. So if A is 1 and also B is 1, then C is flipped. Okay. So if we try to write the truth table for this, as in for what inputs, what output we will get. Let's say these are X, Y, Z. These are the outputs. If we write the truth table, it will be something like this. So there will be 8 possible combinations. Let me write them down. Okay, and so let's try to see what we will get. So remember X and Y, so just as in the C0 gate, if you look at the C0 gate here, so this gate, the C0 gate, the control qubit was left unchanged, so ktex remained ktex. So here also the control qubits will remain unchanged. So X and Y will be equal to A and B respectively. So we can just copy the entire columns over here. So this is what we will get. And similarly for Y is equal to B. So here, sorry. Okay. And now we have to find out what is C. So as I had said that it would always remain the same apart from so C will be equal to Z if in all the cases apart from the case that A equal to 1 and B equal to 1. So you see A equal to 1 and B equal to 1 are these 2 cases. So these 2 last cases. These are A equal to 1 and B equal to 1. So in this case, this target bit, which is C, this C will be flipped. So here C is 0. So since A is 1 and B is 1, here C will become 1. And here it is 1, so this will become 0. And for all the rest of it, it will remain the same. So 0, 1, 0, 1, 0. Okay. And if you want to, so clearly this X is equal to A, Y is equal to B, so they remain unchanged. Now, just as in the last class, we had discussed how to find the expression from the truth table. We will just take the terms with 1 and express it in a sum of product form. So this would be, so the first one will correspond to, here it is 0, 0, 1. So A bar, B bar, C. So A bar and B bar and C. So bar means the NOT gate is applied on it. Or, and the other one is say A bar, BC plus A and B and C, or A and B and C bar. Okay, and if you simplify this, you would get A and B XOR C. Okay, so this is what the topology gets, the third output of the topology get gives us. Or in other words, we can just write this as get A, get B, get C, and you apply the controlled NOT, and this remains unchanged, this remains unchanged, and here you would get A and B XOR C. Okay, so this is how the Toffoli gate works. Now we want a circuit which will give me A and B only. Okay, so what I will do, I'll just put C equal to 0. Okay, so if I just, so in this circuit, if we put C equal to 0 here, instead of C we put 0, then what will this become? This will be A and B XOR C. And XOR, remember, is addition modulo 2, we had discussed last time. So if you add 0 modulo 2 to anything, it will remain the same. So it will just be A and B. So you give A and B in the control qubits and 0 in the target qubit, you will find in the output of the target qubit, you will find A and B. So this is the quantum version of the AND gate. Now I have a question for you guys. Is that in a classical AND gate, how does a classical AND gate looks like? It has two inputs like A, B, and we get A and B. Okay, but here you can see that here we are taking three inputs, like we are putting one input to be 0, and then we are able to get A and B. So can I have a circuit? So my question is, can I have a quantum circuit corresponding to an AND gate with two qubits? Corresponding to AND. So this is my question. In other words, can I do something like this? So can I have some, say, quantum gate? If I'll pass the two qubits, I'll pass, say, A, B, and then I'll get some output like A and B. So can I have this? Any guesses? Yes, no. You can make any random guess also. That's fine. So I can give you a hint. So the hint will be that G, the hint is that quantum mechanics only allows unitary evolution. And this we have learned from the postulates. Okay. So now, do you have any guess? So, okay, let me say that the answer is no. Okay, you cannot have a quantum circuit corresponding to AND with two qubits. Okay, so now, given that I have said that the answer is no, can you guess what is the reason why you cannot have this? Why do you need the Toffoli gate in order to have the AND gate? Why do you need three qubits? If A and B are normalized, A into B is less than 1, the length of A into B. No, look, the length of A into B is inside the kit. So what I mean by A into B is that if I have kit 0 and kit 1, so here A is 0 and B is 1. Okay, so what will be kit A? What will be A into B? A into B will be 0, but it will be kit 0, right? Now kit 0 is normalized, right? So kit 0 is is a part of my orthonormal basis of kit 0, kit 1. These are the eigenvectors of sigma z, if you remember. So yeah, this is A into B is normalized. That's not a problem. And in fact, we are getting kit A into B here, right? In the Toffoli kit also, we are finally getting kit A into B. So yeah, I mean, you are going towards the right direction, but yeah, it has something to do with norm. That is true, but it's not that A into B will not be normalized. Yeah, I mean, okay, yeah, you are actually right. The length of, if I do it like this, then the length of A into B will not be normalized. True, but why do you think that it will not be normalized? Because this is not the reason. Okay, this is not the reason. So why is it not normalized? So what you have to check is that what you have to ask when I am writing a gate like this, you have to see all quantum gates are unitary operators, right? So you have to ask, is G unitary? And you can find that if you try to uh, construct a matrix G which does this, okay, you would find that G is not unitary, in fact. So, and how can you find the matrix G? So very simple. You write the truth table of AND. So let's say AB, and let's write this outputs as maybe CD. AB. So what will be the truth table? So there will be 4 combinations. So C is equal to A, so it will just be the A column. And D is A and B, so this will be 0, 0, 0, and only 1 and 1 will be 1. Okay. So you need a matrix so G, which will take your 0 tensor 0 to 0 tensor 0. It will take 0 tensor 1 to 0 tensor 0. G1 tensor 0 equal to 1, 0, and G1, 1 to 1, 1. Okay. So if you have to find a matrix G which satisfies this, and if you find that, you would find that G is not unitary. And maybe you can take it as take it up as an assignment which you can try to solve at home. Okay, how to find the matrix G given these things. Okay. Is this part clear? Why we cannot have a quantum gate with 2 inputs and 2 outputs, which will give me AND gate? Is that part clear? Because it will not be unitary. So in a sense, what Anmol said is true, that if the evolution is not unitary, then you would not get A and B, you would get some factor, say some 10 times A into B. So basically, it will not be normalized. So in that sense, he is right. So is that what you are trying to say, Anmol? And is this part clear to everybody? Why G cannot, why we cannot have this gate? Yes, no, anything? Okay. So since I'm sorry, my tablet disconnected for a second. Yeah, so since it cannot be done with 2 qubits, we have to introduce an additional qubit and do this kind of an operation to get AND. So, and remember, we already have the quantum equivalent of the NOT gate. So sigma x was the quantum equivalent of NOT gate. So if you pass gate 0 here, you will get gate 1. And if you pass gate 1 here, you will get gate 0. So this was the NOT gate, quantum version of NOT gate. Now, okay. Now, if you remember from Boolean algebra, that not if you have a NOT gate and an AND gate, you can form a NAND gate with it. You can combine them to form NAND. And NAND gate is universal. Universal gate. So basically, you can make I'm sorry, it's the tablet seems to be disconnecting repeatedly. Yeah, just hang on for a while. We are trying to resolve the issue. Okay, is my screen visible and am I audible?
I can see your screen. Yes.
Okay, thanks. So if you remember from Boolean algebra, NAND is a universal gate, and you can create all other classical gates from NAND. So if you have this Toffoli gate, you can create the AND gate. You already have the sigma X gate, which is the NOT gate. You can combine them to have a NAND gate. And using this NAND gate, you can create all the classical gates, like let's say OR, XOR. Although XOR, technically you have already created the XOR gate. If you notice, in the controlled NOT gate, you already have the XOR gate or the addition modular gate. And so this is to answer the question whether we can implement classical gates in quantum circuits. So this is how you would do it. So is this part clear? So in Okay, so now moving on to the basic ideas, some basic ideas of quantum circuits. So in general, you would have n qubit system. So it's a general quantum circuit that I'm trying to describe to you. So if there are n qubits, what will be the Hilbert space? Can anybody say? So for 2 qubits, we have seen that it is the Hilbert space is C2 tensor C2, right? So if there are n qubits, then what will be the Hilbert space? You can also answer in the chat if you like. So 1 qubit, what was the Hilbert space? Can anybody tell? Uh, 2 to the power n will be the dimension, but what will be the, that is right. So Rajrupa says that dimension of the Hilbert space. So let's say dimension of this HS, where this is the system of n qubits, that will be 2 to the power n. That is right. But what will be the Hilbert space itself? So for 1 qubit, can you tell me what will be the Hilbert space? Okay, 1 qubit is, as we had learned a long time ago, is C2. And last class we learned that if there are 2 qubits, then it is a tensor product space. So it would be C2 tensor. Yeah, Anmol, you are right. It would be Cn tensor Cn. That is right. No, it will not be Cn tensor Cn. I'm sorry. That's not right, actually. So 2 qubits is C2 tensor C2. So can you think whether what will be 3 qubits? So 1 qubit is C2, 2 qubits is C2 tensor C2. What will be 3 qubits? Will it be? So Anmol says that it should be C3 tensor C3. But is that right? Because you see, C3 corresponds to a qubit, cube sheet. C2 tensor C2 tensor C. That's right. So this will be 3 qubits. Hilbert space. Okay. Right. So for n qubits, it will be C2 tensor C2 tensor C2, and this will go on for n times. So this is the Hilbert space for n qubits, and this is all often referred to as C2 tensor power n. So what tensor power means is that it's so normal power. What does that mean? Okay, you multiply some, say if there is a number a to the power n, that will mean okay, you multiply it 8 times, right? So tensor a n times. So tensor power means that you tensor product it n times. So this is the Hilbert space for n qubits. Okay. So, and as Rajrupa has already mentioned, so make it small n qubit. So the dimension of the Hilbert space is 2 to the power n. Because you see, I had mentioned to you that the dimension gets multiplied. So for each of this, it is 2, 2. So 2 into 2 into 2 n times. So that is 2 to the power n. Now, if you have such a system with n qubits, then the quantum circuit would look something like this. So initially, you would prepare all the qubits in gate 0 state. So generally, this is the norm. Sometimes in quantum circuits, you can also see that we are starting from some state other than the gate 0 state. But in general, we will start from this state. And then we introduce a series of unitary gates. So let's say U1 and and so on up to, let's say, UN. Okay. So this is a series of unitary gates that we have applied. And then finally what we do is we measure. So we perform a measurement. And this measurement is always in 0-1 basis. Measure in 0-1 basis. By the way, if you remember that 0 and 1 are eigenvalues of, eigenvectors, I'm sorry. These are eigenvectors of the SZ operator or sigma Z, and also since SZ can be written in form of sigma Z, so these are eigenvectors of sigma Z operator. Okay, so we measured in the sigma Z basis, we say, okay, 0-1 basis. And since we are initially preparing in 0-1 basis and then measuring in 0-1 basis, this is a very important basis for quantum computation, and this is called the standard basis or the computational basis. Okay. Now, so this is how a general quantum circuit would look like. There will be initially all the qubits will be in the 0 state, and then we will apply some unitaries, and then we will finally measure. Okay. Now, let's say before all the unitaries is applied, my total system state is gate psi 0. Okay. So can anybody tell me what will be gate psi 0 if all the qubits are in 0 states? So individually they are in gate 0 state. So if I try to write the composite system, like the state of the composite system, so which will be a vectors in this C2 tensor power in space. So So remember, we had last time we had learned about composite systems. So if the first qubit was in state psi and the second qubit was in state phi, we just wrote gate psi tensor gate phi. Gate 0, 0, 0 and it's right. So it would be 0 tensor 0 tensor 0 n times, or you can omit the tensor product notation and just write that 0, 0, 0, gate 0, gate 0, gate 0, n times. Exactly. So this is what the initial state is. And let's say after all these unitaries are done, it goes to some state psi 1. Now, if we know all the unitaries u1, u2, un, then can you express psi 1 as a function of these unitaries? Psi naught. Can you express it like this? So what will be this f? So basically, or rather, let me write it in a better way. So I want to find out what is the net unitary which is acting. So there are multiple unitaries which are acting in sequence. So if I apply u1 first, then u2, then up to un, then what is the total unitary which is acting? U1, U2, UN. So Rajrupa says that it will be U1, U2 up to UN. Okay, let's say that it is U, or let me just write it UM because n is the number of qubits that we have taken. So let's say UM. Okay, so this is what Rajyoga says. But so let's try to write U psi naught. So this means it will be U1, U2, UN psi naught. Now you see that means is the first operator to act on psi naught. But in this circuit, is UM the first one which is acting on psi naught? Oh no, sorry, I'm sorry. It's not what Rajrupa said. It's Aman said that it will be U1, U2 up to UM. So Aman, is this the first unitary which acts on psi naught in the circuit? No. So now can you tell me what? So this will not be U. Okay. So now can you tell me that what will U be? Right. So it will be UM minus 1 and so on up to U to U. Right. So this is what the total unitary would be. So instead of writing this whole circuit, you can just equivalently write. So you have this n inputs, all prepared in gate zeros, and then you have this unitary which is acting on this. So this unitary is basically the resultant of all these m unitaries, which and they are related as this um minus 1, so on and up to u1. And then at the end, what do you have? You have you are just measuring all of them in 0, 1 basis. Okay. So this is an equivalent representation of this circuit. Now, we have said that okay, psi 1, so if you act u on psi naught, you get psi 1. Now, if I want to get psi naught back from psi 1, what unitary should I apply here? U transpose, that's right. So in general, what you would have is you would multiply both sides by U inverse, then you would get U inverse U psi naught, and from there so this would be identity, this would be U inverse, so you would get psi naught, identity times psi naught is psi naught, so psi naught will be U inverse get psi naught. But remember that U is a unitary matrix. So U transpose we know is identity. And from there, you can find out that U transpose is U inverse. So U inverse you can replace by U transpose and you get this. Yeah, it's transpose conjugate. So dagger. Yeah, exactly. So U dagger, U dagger. Yeah, sorry. Yeah. So U dagger psi 1 is what you will get. Yeah, it's true. Transpose conjugate. So it is U dagger. All right. So now you have found this out. You have found out that U is written like this. Okay. In that case, what will be U dagger? Yeah, so not just U1, it will be U1 dagger, U2 dagger up to UM minus 1 dagger, UM dagger. Yeah, I think this is what you meant. So this will be like this. And this follows from, so as Aman was saying, that U dagger was U transpose star, and you know that U transpose behaves in this way, that the order gets reversed after doing the transpose. Okay, so from this, so from that property of transpose of matrices, you this relation follows. Okay, is this all right? Okay, now if you apply U dagger on some psi1, then what is happening? So you have this U1 dagger, U2 dagger. So UM minus 1 dagger, UM dagger acting on psi1. Okay. And so what is the first operator which is acting on psi1? The first operator is UM dagger. Yeah. So if this is the first operator, so if I have this circuit, so if I start with psi1, then in order to go to psi0, so first operator I have to put is UM dagger. And then what will I put? UM minus 1 dagger. That is the next operator which is getting operated. And in a similar way, so you can, it will go to U2 dagger and finally U1 dagger. And at the end, what will you get? You will get, so after all these are operated, you will get sign off. So you see that what this means is that if I can go from psi0 to psi1, then I can also go from psi1 to psi0. And if I have applied the operators in the sequence U1, U2 up to UN, in order to go from psi0 to psi1, then in order to go from psi1 to psi0, we will have operate it in the reverse order, and also each unitary will be dagger. So first we will put UM dagger, then UM minus 1 dagger, and so on. Okay. So what this means is that quantum circuits are reversible, and but you see, once you do the measurement here, then the measurement process is irreversible. So this part which you have here, this is irreversible. Okay, this cannot be reversed. So quantum circuits are reversible apart from the measurements. Okay, let's look at an example then of of the fact that unitary gates and are reversible. So let's take a single qubit gate. Remember, we had the Hadamard gate. Okay, so can anybody tell me, if I give gate 0 to the Hadamard gate, what do we get? And what do we get if we give the input as gate? So you can write in chat, or you can also unmute and speak. 0 plus 1 by root 2. Yeah, this is what you did if you input ket 0. And what will you get if you input ket 1? You will just get ket 0 minus ket 1 by root. And this is ket plus, this is ket minus. Okay, this is what we call. So if I want to go the opposite way, so if I want to start at ket 1 and go to ket 0, or if I want to start at ket minus and go to ket 1, then what should I put here? Is anybody saying something in the microphone? Okay, yeah, H dagger, right. So if it is H, then in order to go from, in order to the reverse computation, we need to put H dagger. Now, H was 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. This was the Hadamard-Kett matrix. Now, if you take dagger, dagger means it is just conjugate and transpose. So all the elements are real numbers, so conjugate will be the same. And if you take transpose, then what will you get? So let's say this is the columns will become the rows, right? So let's take this column. So this first column will become the first row, will be 1 by root 2, 1 by root 2. And again, this second column will become the second row. So this will be 1 by root 2 minus 1 by root 2. And you see that H dagger is exactly the same as H. So it turns out like this will not always be the case. You have to look at the specific unitary operator that you are dealing with. So in this particular case, H dagger is H. So if you just put H here, you will go back from plus to 0 and minus to 1. Okay. Now, having said that, if I operate H 2 times, then what will we get? So let's say I have started with ket 0 and operated H 2 times. What will I get? Yeah, so I'll again get back ket 0. Because you see, H, what does it mean to operate H 2 times? It means the unitary will be H into H or H squared. And we have seen here that H is equal to H dagger, so it will be H dagger. And since H is Hermitian, it is identity. So this is exactly equal to putting identity operator here, or in other words, doing nothing. So if you put get psi here, so which is some general state. So the psi, general psi, remember, is something like cos theta by 2 0 plus e to the power I 5 sin theta by 2 1. If I input this state, then at the output, I will again get the same sign. Okay. So if I apply 2 Hadamard's consecutively. And so this was one gate. Now, remember what we had used for getting the entangled states, the Bell states, from the separable state. We had used this. We had put the Hadamard. We had used it at the control bit, and the target bit was like this. So Hadamard and then C0. So we use this. So let's say again that the state here is psi 0 and the state here is psi 1. Okay, or rather, let's say consider the intermediate state also. That would be psi 1. Okay, let's make this psi 1 and let's name this psi. Okay, so in terms of operators, so psi 1, so you can easily see that it is H acting psi. Or rather, I would ask you, what is the operator that will sit here? Okay, So I have psi naught, the composite system state here, and I have psi 2, the composite, sorry, and psi 1, the composite system after the Hadamard gate. So let me write it properly. This is psi 1, this is psi naught, okay, and this is psi 2. So I want to write psi 1 as some operator acting on psi naught. So can you tell me what operator that will be? Yeah, no, no. See, C naught H will be after the what you are saying is at side 2, like at the position of side 2. I am asking about psi 1. Psi 1 is after, just after you have applied the header method. You have not applied the C naught yet. Okay, then what will be this operator? H. Will it be just H? Because H is acting on the first qubit. Okay, here. But so this is qubit 1, this is qubit 2. So H is acting on qubit 1. But what is acting on qubit 2? H tensor I. That's right. So you have H tensor I into psi naught. Sorry, acting on psi naught. Okay. And now what will be psi 2 in terms of psi 1? Like what operator will sit here? C naught. That's right. And psi 1 already we have is C naught H tensor I acting on psi. And so if you want now to go from psi naught, sorry, from psi 2, so you have psi 2 and you have want to go to psi naught. So what will be the operator that will sit here? Okay, so I think this is also difficult to spell it out in the chat or right. So just I will show you. So remember the order will get interchanged and there will be that. Now already we have seen that H tensor I dagger. So this you can just simply put the dagger inside. So this will be H tensor. Because we have already seen that H dagger is H. And C naught, if you write out the matrix of C naught, which we had done in the last class, you can check that C naught dagger is also equal to C naught. Okay. In the sense that, like this Hadamard gate and C naught, that means they are both also Hermitian matrices or Hermitian objects. So since they are like the conjugate and dagger are the same, then here we will get H tensor identity and P naught acting on psi xi. So that means if you have some state psi 1 and you want to go back to psi naught, then you first apply H tensor identity. That means H on the first qubit, nothing on the second qubit. Oh, am I doing right? Yeah. So, I'm sorry. So, what I'm saying. So, first P naught will be acting. So, first you will get, so after psi 1, you have C naught here. Then you will apply the C naught. And then you will apply at last H tensor identity. So H on the first qubit, nothing on the second qubit, will get psi. And if you want to get back to, so this is what you will do if you want to get back to psi. Now remember that how did we generate the entangled states? So this was the circuit. So this was the thing. So H tensor I and then C naught acting on psi. So H tensor I first, then C naught. Okay. So this gives you, so if you start with 0, 0, which is a separable state, then you end up with the entangled state 0, 0 plus 1, 1 by root 2, which we call ket plus or beta 0, 0. Now, so if you want to go back from this to this, then what you will do, you will just reverse the order. Okay. And we were able to just reverse the order because in general we have to reverse the order and take the dagger. But as we have seen that both C naught and Hadamard, apart from being unitaries, are also Hermitian. And that's why you don't have, like, taking the dagger does not change anything, because for Hermitian matrices, the like M dagger and M are exactly the same. So in order to go from an entangled state to a separable state, you put the C naught first and then H tensor identity. Okay, is this part clear? Any questions in here? When we started n-qubit system, you said psi1 equal to u psi0, but should it not be u tensor cross n times? No. It will not be u tensor cross n times, because you see, this u operator is like this u1, u2, like this u operator is made up of this u1, u2 operators. No? So basically this u1, u2 operators. And these operators are already n by n matrices. Okay. So maybe, so sometimes you might be, so you might be able to decompose, you will be able to decompose them in terms of, so u1 will be some, so 2 qubit, if we take, then let's say, okay, n qubit only. So it will be some u11 tensor, u12 tensor, u1. Okay, so this u1 will be a tensor product. So since already u1 is a tensor product of all this, u2 is a tensor product of all this. So the u that you get after composing, after like multiplying all this, let me remove this. This was wrong. So after multiplying all the unitaries, the net unitary that you get is already like inside each of this, already the tensor product is there. So you do not have to take the tensor product again. Is this clear? Okay. Any other questions still here? So in order to illustrate your point, if you think about what we did in last class, if you go back to the last class, this thing, so you remember we had found out the C naught, the expression for the C naught gate, and this turned out to be like this. Okay. So here these were already, if you see, this was a 4x4 matrix. Okay. So, you know, it's In that case, you don't have to take the tensor product of C naught with something else. Okay. Back to today's thing. Okay, so if there are no other questions, so we will end our discussion today with a small with another important property of the quantum circuits, and maybe dodge dozer we will do next time because there's hardly any time for that today anymore. So yeah. So as also you remember in the when I told you how a general quantum circuit will look like. So I told you that these measurements are all in the K0, K1 basis. So at the end of the measurements, you will get either K0 in some of them or K1. So either K0 or K1 will be measured. So now you can map these to classical bits. So if you get K0, then you will say that, okay, I have gotten the classical bit 0. If you get 1, you will say that we have gotten the classical bit 1. Okay. So the measurement result will be a string of zeros and ones like this. Now we are always measuring in the 0, 1 basis. But what if we want to measure in some other basis, like how to measure in say sigma x basis. Okay, so sigma x basis. So can anybody tell me what is the sigma x basis? So sigma x basis is basically the basis which is made up of the eigenvectors of sigma x. So can anybody tell me what are the eigenvectors of sigma x? Yeah, Rajrupa, you are right. So Rajrupa says that the eigenvectors are 1, 1 and 1, minus 1. Okay, but remember that the eigenvectors has to be normalized because the norm tells us the total probability. So there will be a 1 by root 2 factor. And what is this? You can write it as 1, 0 plus 0, 1, right? So what is this column vector 1, 0? This is get what? So what I'm asking is sigma z, no, yeah, they are the eigenvectors of sigma z. But if I want to write this column vector ket 0 as ket something, what do we write it as? Ket 0, right. So this is ket 0, and what is this? This is ket 1. So basically, and this you can say in a similar way, write as 1 by root 2 ket 0 minus ket 1. And so, and remember, this is nothing but ket plus and ket minus. So the sigma x basis means measuring in ket plus and ket minus basis. Okay. So how can we measure in ket plus ket minus basis when we can only measure in 0, 1 basis? basis. So let's try to look at what measurement in 0, 1 basis means. So let's say measurement in get 0, get 1 basis. What does it mean? Okay, so this means that we have this measurement apparatus. So if I give get 0 to the measurement apparatus, it will give me get 0 with 100% probability. That means with probability 1. And if I, let's say, give get 1, then it will give me get 1 with probability 1. Now, if I have some psi, which is alpha 0 plus beta 1, and of course psi is normalized, so mod alpha squared plus mod beta squared is 1. In that case, what will be the, if I make a measurement in 0, 1 basis, what will be the outcome? So it's a superposition here of 0 and 1. So if you have a superposition of 0 and 1, and if I measure in the 0, 1 basis, get 0, get 1 basis, so it's basically like a SZ measurement or a sigma Z measurement. Okay, sigma Z measurement. Because get 0, get 1 are the eigenvectors of sigma Z and S. So what will we get? Get 0 with probability mod alpha squared and get 1 with probability mod beta squared. That's right. So we will get 0 with probability mod alpha squared and get 1 with probability mod beta squared. Now, what will then, in that case, what will like the measurement in, say, plus minus basis mean? So let's say we have get plus, get minus. So in that case, if you get plus, then you should get plus with 100% probability. Get minus, you would get this. And if you take a superposition of get plus and get minus, then you would get plus and get minus with alpha squared and beta squared probabilities. Okay. Yeah. So now, but so if I had a measurement, device, so let's say some device which can measure in sigma x basis, then that will exactly do this. So basically, this is the sigma x measurement device. But what I have is only the sigma z measurement device. So only in the eigenvalues of sigma z we can measure. So how can we implement this? The sigma x measurement device. How can we implement using the sigma z measurement device? So yeah, and one thing is that so this is I would like you guys to think about this, and next session we would discuss this and go on to the Tosh-Jozsa algorithm. So you can try to think, and the hint here is that we need to add one operator which means plus get to 0 and minus get to 1. Yeah, that is right. That is right. Okay, since you have already given the answer, let me discuss. So basically, what Aman has, Aman exactly has given the answer. Okay, so since you can only do sigma z measurement, then you need some operator, some unitary, which will map plus and minus to 0 and 1. Okay. And can you tell me what this unitary is? So this is the hint. Right. So the Hadamard gate maps you from gate plus to gate 0 and gate minus to gate. And then if you measure sigma z, then say again you would get this. You would get this. Okay. So basically, okay, let me follow the color coding again. Sorry, this is green. So basically what it does is, so if you have a general state also, like alpha 0 plus beta 1, sorry, alpha plus like the superposition of plus and minus if you have, the Hadamard will convert it into a superposition of 0 and 1. And again, you will get 0 with probability alpha squared, 1 probability beta squared. But you see, you might argue that, okay, sigma x was supposed to find, give me output gate plus, gate minus, but it is giving gate 0, gate 1. But you see, you can already always map that, no? Because let's say you have psi over here. Now, if after this whole operation, if you get 0, then you can say, like if you have say 0 at output, final output, then you can say that psi is measured to be gate plus, because you see I am just converting the gate plus to 0 and measuring in that basis. Okay, and similarly if you have say 1 at output, then psi is measured to be in state gate minus. Okay, so yeah, so this is how you would measure in some other basis. So next day I would again discuss this and go on to the Dodge-Jozsa algorithms. So if you have any problems or questions, queries still here, so feel free to ask. And also there is an announcement that tomorrow we will have another tutorial session from 4 to 6. So that will be on this Dodge-Jozsa algorithm that we could not complete today. So any questions? So is it clear what we have done today? Okay, so if there are no further questions, so we will end the meeting today. So tomorrow, that is Tuesday, 6th June, we will again resume this part and go on to discuss the DOS algorithm. Sorry, DOS algorithm mainly, and we will also see the implementation. Soumik will show you the implementation of that algorithm in case. Before that, I will tell you the theory behind this algorithm. Okay, so bye bye for today.
One more announcement. Tomorrow we have talk starting from 9 o'clock. So I hope you all join from tomorrow. Thanks.
Okay, okay. With that, let's end our meeting. Thank you.